Hello there. Today we'll be doing twosum, the array and hashing problem. This goes over the concepts of using a hash and also using sorting that we have done before. So let's check it out. In this particular problem, we are given a list of numbers and a target that we must hit, and we need to return the indexes of where these numbers are. So it's about storing the previous placement of the item. So let's say we see our numbers is 2, 7, 11, and 15. So suppose we are here at 2, that's where I is. We want to store the hash set of 2 and its index 0. And when we're at this particular location, 7, we are going to look for its counterpart, which is 2. And if the counterpart is in our hash set, 0, 2, it is in our hash set, then we can return the current index and the previous index that was found. And that way we return our answer. So this requires us to think ahead about how we will store our numbers that we need and the indexes that we need. So let's try it. So let's say hash set is equal to a dictionary, or just that. Then for I and num in enumerate nums. Theoretically, this will take O of n time and O of n space because it might fill up the entire hash set. Well, yes, it might fill up the entire hash set, and we will be going through all the numbers. So here's the counterpart. We're gonna check if the counterpart is in the hash set. If it is, then we can return the hash set of the counterpart, which is our index, and I. Else, well, actually not just else, we're going to do this every single time, is that we're going to put our num is equal to this current index into it, as we have done here. So with that, we are done with this problem. There's nothing else to do. Let's submit the problem to Leetcode. And this is particularly slow, as you can see, compared to my previous results. And the previous result should be slower because it uses a sorting algorithm, which is n log n time. And for some reason, using a hash set is slower. So the way we're going to do it is to have a left and right pointer. Of course, this is not. This is more extra about our concepts, but I think it's also within bound because it talks about how arrays work with left and right pointers and how sorting an array we can find the number that we need. So suppose that we sort the numbers 2, 7, 11, and 15, left and right pointer. What we know is that when we are here and our target is 9, that if we go up on the left side, every number, the total target is going to always become larger. And when we go down from the right side, the target is, our sum is always going to be smaller. And so if, suppose, we go down this way to 11, our sum is now 13. And if our sum is 13 and it's still bigger than 9, we should keep going down from right. if there are no numbers that we can skip, that is the combination, because whenever we take a larger number and attach it to another large number, it's going to be larger. If we take a smaller number and attach it to a smaller number, it's going to be smaller. So that's the logic behind it. So anyways, we move down and we have 2 and 7, and that's our target. That's how we find where our items are. However, this loses track of the indices of where it originally was. So we will need to use the index function twice. One time to find the number at the left pointer, and another time to find it on the right pointer. A thing is about Python, you can only find the first index of a particular item in the list, and that's another problem because we might find the same indices twice. So what happens then is that we need to reverse the list and then find the index and then reverse it one more time and to get the index. So let's check out this particular problem. I think it's very interesting, and well, this is another thing we can learn about arrays. So I think we did this twice now. The first time was the sorted in anagrams, and the next time we use counter. So this is basically sorted and counters. These are, I think, two very important concepts to take a grasp at when we're dealing with arrays and hashes. Those are some things that we conceptually can use a group of solutions. All right, so let's check it out. All right, so left, right equals 0, and length of nums -1. Another thing is that we need sorted nums equals sorted nums. So while left is less than right, if sorted nums of L plus sorted nums of right is greater than the target, right minus equals 1. Else if this is the opposite case, then if it is less than the target, then we need to increase the left. Else, we're just going to break because we have found our location, and let's get those indices. The first one is pretty simple. We just straight up look for the item that we found. The next is not so simple. So what we need to do is look at reverse the order of nums, then index that particular item. So now we found it. Of course, now we have to reverse that. So and now we can return index 1 and index 2. Wow, that is a very fast time and very good use of memory usage. I don't know exactly how this is giving us these amazing results, but my hypothesis is that the sorted algorithm doesn't actually use more space. What it is actually doing is creating a bunch of pointers to the particular locations that are sorted and giving us a reference to that and pointing at all the items in nums. Probably a very nice optimization. And so this reduces our space from O of n to 1. But as for the reason why it's so much faster once we've sorted these items, and this sorting itself takes n log n time. But going through the items is a lot faster. I'm not exactly sure how this is so much faster, but I think it might have to do with accessing dictionaries. That is taking a toll, because I guess the set of numbers is particularly small. Well, 10 to the 9. Number length is 10 to the 4. Yes. Nums.length is 10 to the 4, which is I think 10,000 like items. So let's see, 10 to the 4th, 10 times 10 times 10 times 10. Yes, 10,000. Only 10,000 numbers. Because if it's only 10,000 numbers, sorting didn't take that long, and we were able to find our items much more quickly using the left and right pointer method. And that gave us this particular answer to this problem. So I think that analysis seems to give some semblance of a reason why this is the case, why this is so fast and reduces so much memory. So in an interview, I think it's particularly impressive if you have the constraints and talk about the reasons why one solution might be faster than another solution, if time allows. So if you enjoyed this video, like and subscribe. If you want more videos, check the link in the description below. Thank you very much, and I will see you in the next one.